So I hope I've convinced you that plants are pretty cool based on how they're able to change the cellular biochemistry that they do depending on whether it's daytime or nighttime. When it's daytime and the sun is out, they can use that ancient bacteria organelle, the chloroplast, to generate the ATP and NADPH that they need and actually can make their own fuels. Then at night, they tap into those fuels and they break them down using biochemistry in the mitochondria, using cellular respiration that we've learned about and those processes to generate ATP and NADPH that they need for cellular needs. Now, we've already talked about the importance of making sure that the Calvin cycle is quiet at night because it's important to make sure that we don't have that futile cycle where catabolically derived ATP and NADPH are used to assimilate carbon dioxide back into carbohydrates that we don't need to be making at night. But another cool thing that has to do with rubisco, that all-important enzyme of the Calvin cycle, has to do with this process called photorespiration. So remember, the purpose of rubisco is to take and assimilate, fix carbon dioxide. So we didn't go through all the details that we have here of sort of the enzyme active site of rubisco, but rubisco is basically going to be taking RUBP, that's one of its substrates, and once it's bound in the enzyme active site, it can deprotonate it, making it into a nucleophile, and then bind and react with carbon dioxide as an electrophile. So carbon dioxide here is the normal substrate. Okay, so the normal substrate is CO2. And then once we fix that CO2, that's how we're going to generate our carbohydrates. So that's the normal process for rubisco, right? But what happens when it's very sunny out is all of a sudden you can have a depletion of the local concentration of CO2. Now, this is problematic for plants because if it's really light out, we've got electron transport that's still happening. So remember, elimination of a substrate is the equivalent of pinching a pathway at that point. So we're not really inhibiting rubisco, but by not providing that substrate, we're blocking the pathway at this process in the Calvin cycle. Now, it's not stopping electron transport from continuing, but what we're then going to be having is all of these accumulated high energy excited electron intermediates, and that can cause what we call photooxidative damage in chloroplasts, and that's irreversible and that can cause death to a plant. So it's really important that if we have depleted this local concentration of CO2, that rubisco still has something that we can give it so that it can do its chemistry. Because remember, if it's light out, all of those signals are going to be telling rubisco to be very active. So what do? We provide rubisco with another substrate. We provide it with oxygen. So not going through all the details of this, but it is a futile cycle in a way. Okay, so we're going to talk about problems using O2. And one of the problems is this circuitous path, and I sort of have it written down here. Here is that RUBP substrate, and we can either have the use of oxygen as an electrophile there or carbon dioxide, and this enzyme is able to do both. But problems with using this, and I'm going to use problems in quotes here, is that even though we're using oxygen, we also need to use ATP. We're not going through the details of what is kind of required for this, but this is going to be a process that uses ATP. And because you're sort of not fixing carbon dioxide, you're not going to be making carbohydrates. And you might think, well, that's problematic. Well, but if it's really sunny out, then you probably don't have problems making ATP because you're having lots of chloroplast electron transport happening. And you've probably, because you've used up all the local CO2, you've already probably made plenty of carbohydrates. So the key is that this is happening when it's sunny, so you're really not going to have issues with making ATP or have already stockpiled carbohydrates. So again, the key is that this is happening at a specific time. So the key here is when, and this is happening when it's sunny. So highlighting again, if it's sunny, not a problem. Lots of chloroplast electron transport is already making ATP. You've got plenty of money to burn. You've already probably made plenty of carbohydrates. That's the whole reason that carbon dioxide has been depleted. Okay, so again, the situations why this happens is when it's sunny, we're going to have a local depletion of carbon dioxide. Okay, but we're going to have lots of electron transport happening. Okay, and that is again going to make sure that we don't have a deficit in our ATP production. But the problem is when we've got lots of electron transport, this can ultimately cause photooxidative damage. And that can be lethal to a plant. So the idea is we cannot be pinching the pathway for the Calvin cycle when it is sunny out. That will cause a backup and accumulation of highly reactive, excited electron intermediates, and that can be really problematic for the health and life of a plant. So find something else for Rubisco to do. Give it oxygen, even though it's a futile cycle, not a problem. So that's photorespiration. Another interesting thing to think about with plants is what we think about in terms of, well, how do you avoid this sort of depletion of carbon dioxide? Especially if it's really sunny out, you're going to have this problem accumulate on a fairly regular basis. So one way that plants can kind of adapt to this is they can stockpile carbon dioxide, okay? And so this is what we call C4 plants. Okay, so how this works, and we're going to go through, kind of zoom in here. There's some enzymes that we're going to recognize here. We're going to take carbon dioxide, and when it's plentiful, so again, this is not a situation obviously that's happening when we're in a deficit. So again, this is going to be when this is plentiful. Okay, the plants are going to bring carbon dioxide in. Okay, we're going to use enzymes. I'm going to star enzymes that are familiar to us. Carbonic anhydrase, right? That's going to take and assimilate carbon dioxide with water and make bicarbonate. Here we've got phosphenylpyruvate carboxylase, right? We've got PepsiK here. Enzyme that we've learned about. We're going to make oxaloacetate, malate dehydrogenase, citric acid cycle enzyme. So we're going to take that oxaloacetate and we're going to make it into malate. That's why this process is called a process that happens in C4 plants, because they're essentially storing and stockpiling carbon dioxide as malate. Okay, so what's going to happen here is you are going to stockpile CO2 as malate, and malate again is a C4 substrate. So what's going to happen is you separate this and you keep it away from sort of Calvin cycle enzymes and Calvin cycle chemistry by putting it in a different cell. So these are mesophyll cells, and that's where we're going to stockpile this malate. So mesophyll cells are going to be very high in concentration of malate. And they actually are going to have a fairly low pH because malate is a carboxylic acid. So we're going to be able to sort of have pH difference that we see in these. Okay, so this is how, when carbon dioxide is plenty, C4 plants will stockpile it as malate. They'll put it in a separate cell, so it's kind of sequestered away from the bundle sheath cells. That's where photosynthesis occurs. Okay, so what's going to happen is when it's sunny out, and if CO2 has gotten depleted, you will take this malate, put it into these bundle sheath cells. You'll have this enzyme called malic enzyme that's essentially going to snip off that carbon dioxide and make it available, even though it might not be available atmospherically. So C4 plants sort of solve this photorespiration issue by separating things in space. So the last thing to sort of highlight is there's another kind of specialized C4 plant called CAM plants, and they not only separate and sequester this carbon dioxide in this way, but they do it by separating in time as well. Okay, so just before we get to that, let me summarize here C3 versus C4 plants, right? Everything that we've learned about prior thinking about photosynthesis is for C3 plants. So most plants are what we call C3 plants. They're going to fix carbon dioxide as GAP. That's what happens in the Calvin cycle. These plants tend to live in very, very cool climates. Photosynthesis rates are slower, so CO2 depletion is not as problematic. So photorespiration really isn't much of an issue. So they don't have those localized depletions of CO2. So photorespiration isn't necessarily a problem. So they're much more energy efficient because they're going to be fixing CO2 and not having sort of that photorespiration piece burning up their ATP. But unfortunately, this can make these plants much less adaptable to heat. And so high levels of heat and light are going to make photorespiration sort of more problematic. And that can really stunt plant growth if you're a C3 plant and you're exposed to too much sunlight. Okay, C4 plants, right? They're going to fix and store carbon dioxide as that 4-carbon malate. That ensures that they're not going to run out of CO2 from having sort of that local depletion. You're going to find these plants where it's very hot and sunny, where you're likely to be having high levels of Calvin cycle chemistry that's going to be depleting local concentrations of CO2. This helps limit that photorespiration piece, because even though photorespiration piece, that piece can be protective for plants, it still can be problematic because it is a futile cycle. Advantages, again, is that you can still have rapid photosynthesis rates even when there's lots of light out, so you're not going to really limit your growth. But again, not being as energy efficient, right? You're going to have that futile cycle that potentially can happen, okay? But storing this 4-carbon piece and kind of stockpiling that CO2 is going to help sort of prevent that. Don't need to worry if you're kind of doing a little bit of extra work to store carbon dioxide in a different space because there's going to be lots of light energy around. You're going to be making lots of energy. So now getting to that CAM plant, this is a specialized kind of C4 plant. So it's called a plant that participates in crassulation acid metabolism. Basically, they do that same production of malate, but they have to think about when they acquire their CO2. They acquire their CO2 at night. And here's the reason why. These plants tend to live in a very arid, dry environment. So their stomata, their pores in their plant surfaces can't be open during the day because they would lose too much water. So they don't bring in CO2 during the day. They bring it in at night. Now, what's kind of neat to think about with this is they don't need to worry about sequestering it in a different space because the Calvin cycle is quiet at night. So they open their stomata at night, they bring in CO2, they fix it as malate. So they basically just have a soup of malate that's sitting there ready for when the sun comes up and can start then taking that malate, liberating the CO2, and allowing the Calvin cycle to do its chemistry once it's light out. So what's kind of neat about these plants is if you were to actually taste them in the morning, they'd be very sour tasting because that low pH from that malate really sort of affects that pH. But as they go through the day and they use up that malate, that pH is going to rise, become more neutral as they use up that malate. So little bit of last biochemistry to think about with plants when we think about the purpose of photorespiration. And yes, it absolutely does have a purpose. And then thinking about if you have or tend towards that photorespiration piece because you're depleting CO2, C4 plants is an adaptive evolution that has allowed them to sort of stockpile CO2 to hopefully limit photorespiration.